Okay, let's jump right into this explainer and look at a truly fascinating method used in modern ship construction. We're exploring a technique that perfectly bridges the gap between what the naked eye can see and what deep ultrasonic scanning can detect. Think about it for a second. A visual inspection is incredibly fast, right? It catches a lot of surface defects. And ultrasonic testing using sound waves is absolutely brilliant for finding deep volumetric voids hidden right inside the steel. But what about the cracks that fall right in the middle? Cracks that are simply too fine for an inspector's magnifying glass to catch, but aren't deep enough to warrant a full ultrasonic scan? Well, that is exactly where magnetic particle testing, or MPT, steps in. It is quite literally the science of making the invisible visible. The contrast here is just stark. Picture an inspector walking the massive steel deck of a ship under construction. Under normal, everyday white light, the weld they're looking at might appear completely flawless. It looks solid, properly fused, perfectly ready for service. But when that same inspector applies this testing method, turns off the standard lights, and switches on an ultraviolet lamp, wow, everything changes. Suddenly, hidden, dangerous surface cracks that were totally invisible just a moment ago begin to glow brilliantly in bright yellow, green, or blue. A weld that looked perfect is suddenly revealed as structurally compromised. So how do we achieve this kind of magic? We have to look at the underlying science.
Section 1. The physics of magnetic leakage. Let's figure out how this actually works.
At the heart of this entire testing method is a concept called a leakage field. When a magnetic field is induced in a piece of steel, the magnetic field lines travel smoothly through the solid metal. But think about what happens when those lines hit an obstruction. Just like water flowing continuously through a pipe, when those magnetic field lines traveling through the steel hit an air gap, like a tiny microscopic fracture or a crack, they simply cannot cross that empty space. They are physically forced to deflect, right? They leak out above the surface of the metal before re-entering on the other side of the crack. This specific area where the magnetism jumps out into the air, that is our leakage field. In practice, this unfolds in a really elegant four-step process. Step 1, the inspector actively induces a strong magnetic field into the steel plate being tested. Step 2, as that field travels, it inevitably encounters a surface or near-surface crack. Step 3, unable to bridge the gap, the magnetic field leaks out directly above the cracked surface. And here is where the absolute genius of the test comes in for Step 4. Fine magnetic particles, which have been applied to the surface of the steel, are instantly attracted to this localized magnetic leakage. The leakage field essentially acts as a powerful magnetic trap, pulling those tiny particles directly into the gap where they accumulate and physically outline the exact shape and length of the defect.
Section 2. The fluorescent reveal.
Now, while you can use dry magnetic dust, the most sensitive and effective variant of this test, especially in shipbuilding, uses a wet method. The inspector sprays a liquid suspension directly onto the weld surface. Suspended inside this liquid carrier are the tiny magnetic particles, but they aren't just plain metal dust. Oh no. Every single particle has been specially coated with a highly sensitive fluorescent dye. Suspending them in a liquid gives the particles incredible mobility, allowing them to flow freely over the steel and migrate swiftly right into those magnetic traps we just talked about. And the result? It's totally stunning. When that UV lamp is switched on, any particle accumulations that have gathered at the defect sites light up as bright blue or yellow-green lines against the dark background of the steel. Because the fluorescent dye reacts so strongly to the ultraviolet light, it makes it absolutely impossible to miss even the tiniest of fractures. Cracks that would have easily slipped past to visual inspection under standard white light become blindingly obvious. As our source notes, under these conditions, even hairline cracks become unmistakable.
Section 3. Material limits and shipbuilding stakes. So, magnetic particle testing is a real hero in the shipyard. It is a powerful tool, but like all specialized tools, it's highly dependent on the material it's being used on. It is crucial to understand exactly where this method can and cannot be utilized. Because the entire process relies completely on inducing a magnetic field, the rules of physics strictly limit its use to ferromagnetic materials. It works exceptionally well on ordinary mild steels and the higher tensile steels that make up the vast majority of a ship's massive hull structure. However, it is completely 100% useless on non-magnetic metals. If you are building a lightweight superstructure out of aluminum, or if you're fabricating specialized cargo tanks using austenitic stainless steel, magnetic particle testing simply won't work. You can't induce the magnetic field, so you can't create the leakage field to trap the dye. Simple as that.
The other crucial point is that MPT has a very specific depth limitation. It relies on the magnetic field leaking out of the surface to attract the particles, right? Therefore, it is exclusively designed to detect surface and near-surface defects. It's not going to show you a pocket of gas trapped an inch deep inside a thick steel plate. This is exactly why it is used as a complementary process. MPT handles the highly dangerous surface and near-surface flaws, while other methods like radiographic X-rays or ultrasonic testing are brought in to handle the deep, volumetric voids hidden far below the surface.
But don't let that depth limitation fool you. On the surface of the metal, the stakes are incredibly high. Picture a ship at sea, bending and twisting under the brutal force of ocean waves. Certain structural intersections bear an immense amount of stress. Magnetic particle testing is routinely used to inspect these exact stress concentration points. We're talking about fatigue-critical fillet welds at T-joints, bracket toes, and the corners of massive cargo hatches. These are the exact locations where catastrophic fatigue cracks initiate while a ship is in service. A hairline crack here, left undetected, could slowly grow under the repeated stress of ocean waves until it threatens the entire structural integrity of the vessel. That is why MPT is mandated as a matter of course in these critical zones.
Let's quickly recap what we've learned about this incredible process. By exploiting the physics of magnetic leakage fields, MPT perfectly bridges the inspection gap between what the naked eye can see and what ultrasound can hear. It uses fine, highly mobile particles coated in fluorescent dye, which, when trapped by a magnetic leak and hit with a UV lamp, brilliantly expose the finest surface cracks. While it is strictly limited to ferromagnetic materials like standard shipbuilding steel, it remains absolutely essential for safeguarding the most fatigue-prone, highly stressed areas of a massive ship.
So, through careful visual checks, deep ultrasound, and the brilliant UV reveal of magnetic particle testing, we've proven the metal itself is sound and completely crack-free. The welds hold, but a weld might be structurally sound, and that leaves us with a massive ship-size question. How do we actually prove that millions of newly tested welds, stretching across cavernous cargo holds, won't buckle and leak under the crushing pressure of the open ocean? Well, that massive engineering hurdle is exactly what we will tackle in our next explainer.